So hello everyone, this is lecture 12 for the mathematical physics, and we were studying the matrices. In the last lecture we completed the symmetric and the skew symmetric matrices, and I told you that how any matrix can be written in the form of the sum of these two matrices. Okay, now let's moving on to the orthogonal matrix. So these are the actually real matrix, and here I will give you just definition. We will study in detail about this matrix. Okay. So if any matrix A is Aij, that is M cross N, its order. If A transpose and A transpose A equal to I, that is identity matrix, then this A transpose should be the A inverse. So if this condition is satisfied, then we call the A is orthogonal matrix. Okay. There is few example for the orthogonal matrix like this and this. Try to solve these both of them by taking their transpose and then multiply. You will get the identity matrix. That's how you can say that these A matrices are orthogonal matrices. Now, in the complex plane, just like we have symmetric, skew symmetric, and the orthogonal matrix, in the complex plane we have Hermitian, skew Hermitian, and the unitary matrix. Okay, these are just analogy. Okay, and what are Hermitian matrices? So if there is any matrix A, okay, that is Aij n cross n, these are square matrices. Okay, then we need to find the A dagger. We call the sign as dagger. So A dagger will be first take the conjugate of this matrix, then take the transpose. First conjugate, then transpose. Then the matrix you will get, that will be A dagger. Okay, so if A dagger came out to be equal to A, then we will call it Hermitian matrix. Okay, and if it came out to be minus A, then we will call it skew Hermitian. Okay, now let me just told you, if you don't know, that what is the meaning of conjugate. Conjugate means if you are having any iota term inside the matrix, then it will just turn to be minus I. Okay, and the real will remain same. And transpose, you know that the row to column interchanged. Okay, so there are some properties. If in the Hermitian, let's see, this star is also represent the conjugate. Okay, so we know that when we take the transpose, the diagonal element will remain same, means these position won't change in the Hermitian matrix. Okay, so if A dagger came out to be A, then these diagonal elements should be free of imaginary number. Okay, because conjugate will give you minus I, so these will not remain same. But if it is Hermitian matrix, that's why these diagonal element will always be real, no imaginary part will be here. Proof is also here. You can see that this conjugate should be equal to this. Okay, and for II means for the diagonal elements, AI star should be AII. Okay, means conjugate will be equal to the original number. That this is only possible when the diagonal elements are real and not imaginary. Okay, if there is IA available in the diagonal element, then that will change to minus I, so it won't remain same. Okay, that's why diagonal elements in the Hermitian matrix is always real. Okay, and we can take this example. If this is the matrix given, then first take the conjugate. This will turn to a plus, this will turn to a minus, then take its transpose. This 4 minus, this will came out here, this will came out here. Now this is nothing but same matrix as A, so we call this matrix as Hermitian matrix. And you can see these diagonal elements are real, no imaginary part is here. So all Hermitian matrix have diagonal elements real. Okay, now skew Hermitian. Here we can see that the diagonal elements, or the basic definition is this, that A dagger should be came out to be minus A. Okay, and you know that in transpose the elements position remains same, that's why we are considering only the diagonal elements. Okay, so for that, if I equal to J, then this should be this. So if you take the sum, then A II element should be 0, means the real part should be 0. Okay, in the skew Hermitian case. and the transpose will remain same and minus sign will came out only if the diagonal elements are imaginary. So you can just check this with example, that just take any matrix like this. Well, this is a different thing. So you can take the example, then you will find that in the diagonals you will get only the imaginary numbers, because when you take the transpose these will remain same, and the real number can't be equal to the minus sign with minus sign. That's why we don't get any real number in the skew Hermitian matrix in the diagonals. Only the imaginary part is there. Take it like this. Well, if there is no imaginary number inside a matrix, then skew Hermitian will turn out to be skew symmetric, and Hermitian matrix will turn out to be symmetric matrix. Okay, means skew Hermitian will turn out to be skew symmetric, and we know that in skew symmetric diagonal elements are 0. So here also real part is 0 but imaginary available. Okay, same here. In symmetric matrix the diagonal elements remain same, so we only have the real part. Okay, no imaginary part inside this. So just try to solve these matrices and you will get the idea what I am trying to say. Otherwise I give you enough I have to explain this. Now there is a third matrix, that is unitary matrix. Okay, so just like the orthogonal matrix, here we have unitary matrix in the complex plane, and this is nothing but if a dagger a equal to I and a dagger, means now a dagger should be equal to a inverse. So if this condition satisfied, then we will call it unitary matrix. Okay, so this is the condition. Just take its conjugate first. It will turn out to be minus I by 2 minus I by 2. Okay, then take the transpose and then multiply that matrix with this a, you will get the identity matrix, and that's how we call it unitary matrix. Now we just defined some special matrices. Now we will see the application of these matrices, means how we can use the matrix to solution of linear system of equations. Okay, so first we will discuss the Gauss elimination and back substitution method. Okay, so what is this method? So consider a linear system of m equations in n unknowns. So just like you have seen the equations x plus y plus z equal to something, 2x plus y plus 3z equal to something, that's how we can take m equations are there. M equations are there with n unknowns, means n variables we have with m equations. Okay, so just like this we have first equation, second equation, third equation. That's how we have m equations, means this is mth term, and variables are how much? N variables. So that's why x1 x2 xn. So now all x1 have power 1, means these are linear equation, and when we call it linear, the powers of these variables should be 1, and a11 a12 are some constant called coefficient of the system, means these are the coefficient of the system, and b1 b2 b3 means ye wale, this one, these are also constants. Okay, now we can represent these equations in the form of matrix. You already studied this in the elementary classes. Now we will see some big picture. So now in these equations, if all bi's are 0, means all equations have 0 in the right side RHS, then it is called a linear homogeneous equation, means x plus y plus z equal to 0, 2x plus 2y plus 3z equal to 0. That's how when you have the 0 in the right hand side, then you will call it homogeneous equation, linear homogeneous equation. And if there is at least one bi is non-zero, that if any b came out to be non-zero, then it will be non-homogeneous equation. Okay, now the solution of equation is a set of numbers. If we consider this one equation, then solution of these means x1 x2 x3, the values of x1 x2 x3, that satisfies all m equations, means these solutions will satisfy all these equations. Okay, you know that. Now if the equations are homogeneous, then there will be always one solution is always available, that is trivial solution. When x1 equal to 0, x2 equal to 0, all equal to 0, means you can say that x plus 2y plus 3z equal to 0, then x y z can be 0 0 0. So that is trivial solution. Okay, so this solution will always be available for the homogeneous equation. Now we can represent these equations in the form of this matrix. Here we can represent A matrix by this X matrix, where the variables are there, n variables, m equations, and in the RHS we can represent this B matrix. So we can write these system as Ax equal to B. Ax equal to B means just multiply with this, you will get A11 x1, A12 x2. That's how equal to B1 and second one. So you can just write this system as this. Okay. Now let's see what is Gauss elimination method. So before that, we see that there were m equations and n variables. So if equations are more than number of variables, then we will call the system as overdetermined. Means you can find the solution easily. And when m equal to n, the number of equations are equal to number of variables, then you will call this system as determined. And when a number of equations are less than number of variables, then the system will be underdetermined. Okay. So, and this system is called consistent if it has at least one solution. Means if these equations, when we solve them, and then if at least one solution is available, then we will call it consistent. And if no solution is available, then we will call it inconsistent. Okay. Now there can be unique solution to these equations, infinitely many solutions to these equations, or no solution at all. So we'll find this. How we can find this? Existence and uniqueness of solution. So these three types of solutions are possible. So let's see how to solve these matrices with this Gauss elimination method. Then we will discuss this all three parts. Okay. So first, if any system is given, first we will write the augmented matrix. And augmented matrix is nothing but you can write in this form. Means this. All the coefficients will be in this space, and the right hand side will be here, b1, b2, bm. So that's how you can write the augmented matrix. Just keep it in mind how you write the augmented matrix. Hope it is easy to understand. Just this and this one, just write 2 with this dash line. So this is the augmented matrix. First you have to write this, then this matrix can completely determine the system 1. Means the system we have seen here, this whole system can be determined by this matrix. Okay, now let's see how we can find the solution with this type of augmented matrix. So first write, let's see, there is example 2x1 plus 5x2 equal to minus 4x1 plus 3x2 equal to minus 30. So write augmented matrix for this system, that is 2 5 minus 4 3, and the right hand side 2 minus 30. Okay. So here what you have to do is first take this element as pivot element. Okay. So for the first row, the first element will be pivot element, and just try to make the element lower than this as 0. Okay, using the elementary row operations. Okay, so how you can make this 0? Means you can add this equation to this equation by multiplying 2 in this equation. Okay, so R2 is R2 plus 2R1. So what you will get? Minus 4 plus 4 0, 3 plus 10 13, minus 30 plus 4, that is minus 26. So that's how you will get this. Now you can see that here we have x2, 13 x2 will be equal to this, and x2 will be minus 2. And when you get x2, just substitute it back and find the x1. So this is called a back substitution. Means first you will get this row with single variable, and you will get the value of that variable, and then you back substitute this in this equation, then the second variable. So that's why we call it the Gauss elimination and back substitution method. So first you will get 13x2 equal to minus 26, x2 will be minus 2, then 2x1 plus 5x2, here substitute the value x2, that is minus 2, and x1 will be 6. So hope you are getting the idea what I am trying to convey here. Now let's take a little big example. So this is the equation given. These 4 equations are given. So just make the augmented matrix, that is 1 minus 1 1, minus 1 1 minus 1, then 0 10 25, then 20 10 0, and in the right hand side 0 0 90 80. Okay, so just first take first row and this one as the pivot element, and try to make the 0 lower than this. All should be 0. Okay, so how you can make this? Just add this row in this row, means r2 will be r2 plus r1, and r4 will be r4 plus 20, r4 minus 20 r1. So just apply these operations in whole row. You will get this, and the fourth row you will get this. So you will get here zeros, and now you can see that we get this one as 0 0 0. So we can just interchange this row, means we can put this row in the last and just make these up, means just see this, the solution won't be affected if we solve this equation first or this equation first. That's why we can write it like this, means take both of them in the upside and take this 0 in the downside. So we get this type of thing. Now this will be the pivot element and make this 0, then you will get this type of situation. Now when this will be 0, now you will have this, so you will get the single variable here now. So you can now solve this equation for the solution, like minus 95 x3 will be this, and x3 will be 2 from here. Then put that x3 in this equation and find the x2, then x2 x3 put in this equation, then find x1. So this is elimination and back substitution. So that's how you can solve these equations. So I hope it is easy. And if you get this type of system in the augmented matrix after making these eliminations, then you will call it the unique matrix, means you can find the unique solution from here. Okay, so from by just seeing the augmented matrix you can determine if it has the unique solution or not. Okay, I will tell you how you can determine for the no solution and the infinitely many solution, but just here just see for the unique solution. So this type of matrix will show you the unique solution. So one more example, that is x plus y minus z equal to 9, and this and this. So just the augmented matrix will be 1 1 minus 1 0 8 6 minus 2 4 minus 6, and right hand side 9 minus 6 40. Okay, so take the pivot element this one and make this one 0. So how you will make, that is r3 will be r3 plus 2 r1. So this is this like this, then this one will be the pivot element, make this one 0, and you will get this type of matrix. So now it has unique solution because you are getting how the unique solution works. So in the next lecture we will discuss how we can say that if any matrix has no solution or infinitely many solutions. In today we will end here. Okay, just revisit the lecture, and if you are having any doubts then put in the comment section, or you can talk to me in the Telegram channel or group. Okay, thank you.